back to the stream, everyone. Tuco's starting us off with some high-quality meows and yelps. What do you want, little dude? There's some quality cat and power tool juxtaposition. What do you want, little dude? Okay. There's some quality cat and power tool juxtaposition. What do you want, little dude? Okay. Alright. You can start this off with a little bolt. Cat and power tool juxtaposition. So welcome back. I've got a little Sanrio Labs hardware investigation here. This is another look back into these sort of network-connected webcam devices from D-Link that we were looking at a little while ago. A little Sanrio Labs hardware investigation. In that stream, it was for the context of just adding a serial port to a bunch of them. These sort of network. But in this case, we'll be taking a close look at one of the devices, and specifically, we'll be looking at the connections in between the chips. Just adding a serial port. We'll be talking about that more later, but how in-depth we go into that might depend on how interesting the connections are on this particular camera. And specifically, we'll be looking at the connections in between the chips. We'll be talking about that more later, but how in-depth we go into that might depend on how interesting the connections are on this particular camera. And specifically, we'll be looking at the connections in between the chips. Is that one not interesting? How in-depth we go into that might depend on how interesting the connections are on this particular camera. Is that one not interesting? How in-depth we go into that might depend on how interesting the connections are on this particular camera. Tingo, you just made that harder. Did you push that under the rack? It went all the way under. There'll be a stream in the near future about the rack, but so far that has not been the way to go. You just make that harder. Did you push that under the rack? It went all the way under. There'll be a stream in the near future about Oh, thanks for the link in the chat, Sodium. I should really set up a bot to do that, but in the meantime, it's really nice to have some help. Oh, there's an echo. Oh, did that maybe start up in my, I should really set up a bot to do that. Let me put the headphones on. In the meantime, it's really nice to have some help. Sorry about any technical difficulties. I just changed around some of the audio setup today. Echo. Oh, did that maybe start up in my, I should really set up a bot to do that. Oh, do I not even have headphones here? Sorry about any technical difficulties. I just changed around some of the audio setup today. Oh, did that maybe start up in my, usually I can monitor this with headphones, although for some reason the headphones that were working just a second ago no longer are. So that's a little concerning. Usually I can monitor this with headphones, although for some reason the headphones that were working just a second ago no longer are. So that's a little concerning. The VU meter on the stream is working. I can't actually tell if you can hear anything because my headphones are totally dead right now. Wow, sorry for the audio amateur hour today. The VU meter on the stream is working. I can't actually tell if you can hear anything. Well, I'm going to go and make sure nothing else is playing in the stream, just to make sure that isn't echoing for all of you. It could be down here, except it isn't. Just to make sure that isn't echoing. Okay, apparently I am audible. My monitor is just not working. That's weird. It could be down here, except it isn't. Just to make sure that isn't echoing. Okay, apparently I am audible. My monitor is just not working. That's weird. I think the Twitch stream was open on the other computer, which I didn't even know was being routed over here since I can't hear it, apparently. You know, I think the output amplifiers and our audio interface are heating, because I can't hear anything, but that's fine. Yeah, it looks like the audio's fine. I'm 60% crackle now. And echoing. Well, at the risk of making everything terrible, let me see if I can actually reset the audio just to get a sense of what this even sounds like. The audio interface. Oh, resetting the audio interface seems to have fixed it. I can hear myself now. Let me know how that is on the other end. I think I may have had some problems with the audio interface getting a little warm because unintentionally I had, well, I had left the window curtains open here such that a sunbeam was hitting it right in the middle. So, yeah, I think it might take a sec. I tried blowing some compressed air in there, but it might take a little while for the temperatures in there to equalize before it behaves completely normally. So, okay, I didn't have to reboot Ableton or anything. I just had to restart the audio interface. And Tuco really wants a bolt. Oh, thanks for helping me debug that. Thank you. Tuco. I guess I didn't throw it just right. Yeah, there's a lot about my setup that's currently kind of super not optimal. Like, I'm in the process of moving that into that, which should help a lot of things. But right now it's kind of a mess still. I haven't had the time to actually commit to doing the move. There's the UPS on the floor. It's incredibly heavy. To be fair, this audio interface usually runs really, really warm. And I can imagine how it being painted black and being in the sun while also really, really warm is probably not so good for it. So I felt bad, but I doubt that I damaged anything permanently. Anyway, it looks like Tuco's got a challenging bolt over there. Let's see what we can do on this end. So welcome back to the stream. I added a tiny bit of delay on, well, so there's already some processing delay on the camera, of course, but I added a little bit of extra to try to line it up better with the audio on the stream, which means it's even more laggy for me, but it should be better for you. Let me know if you notice anything. But anyway, this is the camera we'll be working on. We had this on stream before. Oh. There we go. Let's start that up again. Tuco. Little cat's having a difficult bolt over there. I've been throwing him some bolts to get the day started, but that one went. There's like a little stash of boxes over there, and then there's a push broom. Tuco's fighting the dust bunnies for it, but I think he won. Good job, little guy. Good job, Tuco. It's spoils of his fight there. Delicious, delicious nylon quarter 20. Good Tuco. All right. So these were on the stream previously. Also featuring brand new anti-static matte, which I feel so much better about since I've been very conscious about how these tables are really good static electricity generators. So I've been careful to ground myself and wear the straps, but now at least I have a static dissipative surface with a nice like grounded surface, and it's nice. Definitely recommend this if you are taking apart devices that it would be really, really good for you to not destroy. Because, you know, there's always a risk that you can zap the wrong chip on the wrong I/O pin that isn't really well protected. And using proper static precautions greatly reduces that risk. Hey Tuco, what do you want, little guy? You under the table. You are extremely under the table. All right. You want that? Yeah, okay. He is so into that. This is his favorite game. Okay. So we were in these devices before, as you can probably tell. So previously, I had a little video. In fact, I made a little video montage of just taking these things apart, identifying some of the interesting chips, and then identifying the serial port and then soldering these little 4-pin serial breakouts to a whole pile of them, like 30 of these. So this time I think I want to probably, just to make this easy, I think it might honestly be easiest to deal with if I just temporarily desoldered all of this. I took this one home from the workshop because it was already broken. So it might be easiest to get inside this if I just finish taking the rest of the wires off, and then I can just take this front cover off without having to deal with the rest of the, you know, without having any more mechanical complications there. So, oh yeah, I also really like the aesthetics of this mat because I didn't want it to be brightly colored because that messes up a lot of photography that I would want to do otherwise. And having a very light or very dark color also tends to make it really difficult to get the right dynamic range in the shot, so this was actually just right. Okay. That is so his thing. All right. So it was this side that comes off. And so as we saw before, this thing is just one circuit board. It has, well, one main circuit board. It has this kind of other thing that is like a circuit board, but it only has, it's mostly a mounting for LEDs and the moves filters in and out in front of the lens. All the components we're going to be interested in, are on this circuit board that's basically the same shape as this enclosure. And there's some tricky little snaps in here, which this is partly why for most of these I didn't actually ever open it up. Just use the hot knife to make a hole right in front of the connection that I wanted, because the snaps on these cases are kind of annoying. It's hard to do this without messing up the plastics a little bit, especially if you don't know exactly where the snaps are. I kind of vaguely remembered from the last time I took these apart. Oh, Ryan's asking if I happen to have a link for the mat. I don't remember. It was pretty easy to find. I remember I found it by searching on Amazon, and it was, I was looking for inexpensive mats, and the two, well, this was not that inexpensive, but it seemed to be worth the additional extra relative to the really, really cheapest ones they had. So that was basically how I found it. I was looking at the really cheap ones, and then this one seemed like a pretty decent step up. But I don't remember the manufacturer off the top of my head. Just trying to not mangle this too much, but... And the servo AF is keeping up a little bit. Oops. Probably helps that I'm not zoomed in super much right now. Alright, that's what we wanted. So it looks like if we start taking this off, it's going to take those wires with it, so let's go ahead and desolder those. Oh, we don't need the black box up there. Hey, Tuka. You are an amazing lab cat. Whoa, such beep. I find myself lining this up to the monitor, which is then very, very different from what's actually on the desk. Well, let's fix that. That's better. This should be a quick little takeoff. Where's my tweezer? That's what happens when I clean up my tools. Oh, these will do. Oh, I guess I've got the other soldering iron plugged in. That's fine. What does that even mean? What does that even mean? Excuse me. I don't even know what's ringing up there. My phone was on silent, but I just reinstalled macOS on my laptop, and I think my laptop upstairs was ringing. Good one, laptop. Alright, these wires are now safe. Let's take a look at the rest of this. So I think we can gently pry this open without breaking anything. So there's our cover with 4-pin breakout. There's the goodies. This is held in by one screw. No. Why would that be happening? I don't know about you. Does anybody else really dislike voice calls? Like, who thought it would be a good idea to make this machine that can just bother you at any time and expect you to actually talk to someone? It's like, no, that's terrible. That's not why I have a phone. It's not for that. Alright, so we've seen this part before. So this over here is the camera processor. This is the really little camera chip. This is the serial flash, which we'll definitely want to take a closer look at. This is the application processor and Wi-Fi system on a chip. There's the RAM. And this is some power supply stuff down here. There's some inductors. U1 is potentially a switching controller, although it's not right next to the inductor, so I think this is the switching controller actually, and that might just be an additional linear regulator or switch. There's another part over here that might be power supply type stuff. Oh, TI M5P. That one's right underneath the camera processor chip. That one's probably something kind of analog related, but we should take a look at it. And then this board, all of this stuff is kind of related to the, you know, the electronics and the mechanical process of actually driving the LEDs and the shutter. Oh, man. This is probably another Amazon delivery driver that's lost because the signage here is terrible. And it's just, oh man. I can usually go out there and help them find the right spot, but like, they don't really have a good like way to I don't know, like there is a sign that tells people outside where the deliveries are. It's not easy to find, but it's there. And you'd think that if they had the same people service the same area, that maybe they would know where to put the packages. So we looked at this board before. Most of this seems to be related to actually driving the current, like driving the current through these LEDs, driving current, both directions through this coil to flip it either into the infrared filter or into the non-infrared filtered mode. And then I think this is just an amplifier for the light sensor. So if we're looking for communication buses, I don't think we're going to see anything digital on this board. So I might as well unplug this board for the moment. Oh yeah, as Emily mentions in chat, voice calls are especially, so like there are several things that I think make voice calls just like bad in general, but then there are also reasons that they're bad if you have social phobias, and there are reasons they're bad if you're trans, and all those kind of compound with each other. Yeah. So I don't know, that's partly why I like computers. You can find business that you don't have to talk to people about. I'm just kind of basking in the glamour shot of this board and not even caring that it's upside down. I mean, upside down. I guess I wanted the label on the camera processor to be right set up, but now the labeling's on the silk screen are upside down. So we looked at this a little bit on the last stream where we were investigating these cameras. There isn't a lot around here except for the two main processors and some memory as far as I can tell. So over here is some WinBond memory, which is almost certainly SPI flash. We can look up how much that is. But I think at this stage, let's go ahead and maybe make a diagram starting to lay out where all these parts are and what they're doing to each other. I don't know exactly how this chip would be communicating with the application processor. My guess is either USB or something more specialized, like I think there's a camera bus called CSI that they might be using. It might be some kind of LVDS, but probably not something easier than USB to sniff at. And then if we look at the other side, so this is the main processor, this RA-Link RT3352. This is going to be RAM. So the reason I know that is partly because the kind of shape of the chip and the manufacturer are really typical for RAM, but also because you see all these parallel traces going between the processor and the RAM. That's a high-speed parallel bus, which you would really only need for something like memory or a coprocessor or something where you are exchanging a lot of data really quickly. You can also see that there's some length matching going on with these squiggly traces. That's to ensure that when you have a byte of data or a word of data split across into many lanes, they all arrive at the same time, roughly. There's maybe some question marks here. So, the RAM, there are commands you can send to the RAM, but ideally, really what we're looking for here are trust relationships between the components. So if we're looking at this from the perspective of, how can we gain information about how the firmware works? How can we create privilege escalations to demonstrate vulnerabilities? What would an attacker maybe try to do to the system in various scenarios? For those kinds of questions, it really helps to look at the trust relationships between the components. So obviously, if you have a processor reading code from an external chip, there's a trust relationship. So memory chips are a great place to start. Not DRAM necessarily. You can use the DRAM. In fact, I've got a project a while ago that would be fun to talk about sometime that exploited the trust relationship between the processor and the DRAM to get code running inside of some firmware that otherwise wouldn't allow code execution. But that's really tricky because of all these high-speed wires. It's much easier to exploit the trust relationship that you have on a chip like this. This is a serial a serial EEPROM or serial flash memory chip. So in this case, what's probably happening is that there's firmware in some kind of ROM or a hardware state machine that is just pulling data in from here onto, into RAM on this system on chip and then executing code eventually. There are a handful of different ways that could work. You could have different levels of hardware assistance, different parts of it could be implemented in software. But some of those implementation details will be a little easier to see either by reading the manual for this chip, because that might give you a clue for how this is implemented based on what hardware is available, or just by looking at the timing and kind of sizes and things like that, just kind of the meta information about the transfers that we see here. You can get a lot of information about what the structure of the hardware might actually be, and whether those requests are coming from hardware or software, and what kinds of processing might be going on between requests. There isn't a lot else. There's a couple of these little chips that might be interesting to take a look at. So some of these are obviously just like power supply related, like that one and that one are definitely going to be switching power supply controllers because they're right next to inductors and capacitors. Same with this one. This one is probably something power supply related. There's not really much you can do that would have an interesting bus on it in 3 pins. So you can usually ignore the 3-pin ones if you're looking for buses. There can be exceptions, but usually not. So we definitely want this memory. We'll take a look at what the bus is on the camera chip, but it's likely something fast and kind of annoying to sniff. It might be USB, in which case a little bit of circuit board surgery and an off-the-shelf USB analyzer, and you've got a tool to debug it. Then on this side, I'm curious about U5 down here. I think we should try to look that one up. U3 over here might be interesting, but it's probably power supply. If you look at these big capacitors on 2 sides of it, that's probably a regulator of some sort. This one has so many capacitors around it that it might be something power supply related too, but it also might be something analog. So it's probably not going to have an interesting bus, but I'm kind of curious enough that it's worth looking up the number a little bit. So where was that in this giant view? Oh, I'm not quite caught up on chat, but I guess there's some question about whether that WinBond flash contains the whole system, or just like configuration, or just the bootloader. I don't see any other flash in the system, so I assume that would have to contain the whole firmware unless the ARIA link has flash on board. So we'll find that out when we look at the datasheet. I mean, somebody in the chat might just know off the top of their head, but I was going to look at the datasheet for the main chips. So that's the processor. We briefly looked at the datasheet last time, but or maybe it wasn't on stream, maybe it was just really briefly in the edited video, but still, that deserves another look. And then just while we're on the microscope, here is the camera chip, OV00780. And here's the flash. Q64BV. Why is my computer screen not working? If I had that going, I could probably look up how big this was. Wake up, computer. On buttons. There's supposed to be one of these that has them side by side. There we go. An owl chip. Sorry, I'm a little behind on the chat on this stream. I think there are a lot of questions going by that a lot of people probably have good answers for, but I'm falling behind on some of them myself. I mean, if you're going to fill in the suffix for me, sure, but I don't think I actually want. Q, F4. I mean, I think this is just a different package, but... Oh, this looks like it. Huh. 64 megabit. That's enough for the whole system, probably. That's 8 megabytes, which, you know, a firmware and a really small user space. I mean, we had a serial console, so we could just check how it's configured there, too. There are a lot of different ways into this particular system. But yeah, this might be handy. Let's save that for later. So then, I guess while we're here, let's pull up the datasheet for this and just see what kind of memory it has internally, if any. Product brief. That's not necessarily what I wanted, but... Oh, this has an Ethernet switch in it, too. That's handy. Yeah, this doesn't seem to have any flash. Has 2 SPI flash interfaces in hardware. So this is probably going to just map the SPI flash into memory somewhere, and then it's going to run some amount of boot code, execute in place from that really slowly, and then that's going to copy the relevant parts into RAM, probably. So I think that's fine. Oh, yeah, thanks for letting me know about the audio. That's always good to know when there's a problem or when there's not a problem. Okay, so those, I can save those in our pocket for the moment. Let's go ahead and check out what the interface to this camera chip is. I think I had the datasheet for this up previously before, but it was also not very... I don't even know if this will fit on the microscope. Yeah, I'll just make some attempt to have this over here. Is this OVO780? Yeah, this might be one of those kinds of camera chips where you don't actually end up finding real data sheets for them. I don't think any of this is real. Well, we might just have to look at where that's connected or how it shows up under Linux. Because, you know, as we said before, we do have access to the system's console. We can pretty easily poke around in there. So, let's just take a look at that one mystery chip and then figure out where to go after that. Is that actually going to be Texas Instruments? Doesn't look like a Texas Instruments chip really, but let's see if anybody just has these markings. M5P. Don't know if we're actually going to find a number for this chip. We might just have to look at how it's connected. Yeah, not so much. Okay, how is this thing connected? Let's see if we can get some more contextual clues. So, is it maybe an op amp? This black solder mask is not helping. I'm guessing it might be something related to the power supply for the camera. Is that a big surface mount inductor that is not, why does it say, oh, that's the little chip, that L11, sorry. No. I mean, it smells like a power supply. My guess is that it's just an LDO providing some local voltage for this camera processor, because it's right under the camera processor. And we're not seeing a data sheet. Maybe if we knew what this was actually called. I mean, we certainly got a better number for it under Linux, and Linux would tell us how it's connected, so maybe we should just boot it up. Oh, Chris in chat says that that chip, mystery chip is probably an LM358 op amp. I believe that's an op amp, right? Let me double check that. Yeah, that's a dual op amp from TI. Do they have maybe marking info in the datasheet? They have a lot of packages that aren't this. This is fancy. Well, this is probably some variant of this. Okay. Well, I assume that's something either analog or power supply related in the camera that isn't going to have an interesting bus. Which buses could the camera be on? So this is, again, the application processor. I strongly suspect the camera is going to be USB, because it would need to be fairly fast. You know, it's not going to be I2C or I2S. It's probably not SPI, although it could be. It might be just something weird, but... And this doesn't seem to have any, like, dedicated camera interface hardware. I don't know. I think we should briefly take a look at it in Linux. Oh, okay, there's a TI part lookup that Chris linked to that we should take a look at. Oh, this looks really handy. Let's see if this works. Let's just try it out. Ti M5P. Oh, nice. So I guess that's how TI does theirs, but every other manufacturer is going to have a different scheme. Neat. Okay. Well, that is really good to know. Well, okay. I think we know what the next experiment is. Maybe let's try... My inclination is to hook up both a regular serial console and put the Oscilloscope on the flash memory and the serial, so we can see it boot. We can see the order it accesses the flash memory in. And then once it's booted, we can check to see how the camera is connected. Okay, so for that, we're going to need like just a few more connections than what we already have. Let's get ourselves a good header on here so we can tack some wires down. I wonder where the cat's hanging out. Okay. So, alright, so the original plan here was to try to make a block diagram, but it turns out that, well, there aren't very many pieces that are actually talking to each other, and we don't know a whole lot about it other than that the firmware is in that SPI flash. So it'd be nice to know exactly how the camera chip is connected. It'd be nice to know a little bit more about how the flash is being used. So, well, let's just make ourselves a little connector here. So we'll want a pencil that can write. Well, at least a ground. What else is handy around here? I think somewhere around here I have an SO8 clip that would clip right onto that memory chip. Oh, you know, actually, this memory chip is huge. I was thinking I'd have to solder some magnet wire to that, but actually, I think I've got micro grabbers that'll just fit right on there. So we can just clip on there and get that on the Oscilloscope, if that would ever focus. So yeah, these legs are huge enough that I can just clip some grabbers on there. So I think this experiment we want to use the salient analyzer or something like that. I didn't even get up to Cigarock. Yeah, the information we mostly want is going to be the timing of these SPI reads. Oh, the audio is crazy again. It seems like the same problem. Maybe this is an issue with the USB controller on this computer. Check. Is that any better? Check. It sounds alright in the headphones now. Let me know if that's any better on the other end. My headphone cable is just very tangled. Alright. I guess I can wear these for a little while. Alright, I'm just assessing what the minimum fuss way of doing this is. Maybe I'll just solder on something else to the serial port, like another little set of 4 pins. It just is not epoxy down to the other case. And then we'll be on our way. Not that camera. Oh, this is what I wanted. Alright, same old thing. I like Peter's suggestion that we should have like a timer in the chat counting down for when the messages actually show up on the stream. Yeah, imagine actually having some infrastructure for that. Oh, I did actually try out the YouTube mobile chat client. I hadn't seen their iOS app integration. It's kind of handy. I agree that would be one reason for sure that the bridge could be useful if we were to have such a thing. Is that a car alarm? No. Just using a little bit of flux so that I can solder onto these without them staying all sticky and gross. That was definitely a real noise. That one was the, actually, I don't know whether that was the FedEx or the fire station. It was somebody's, like, truck thing. You know, trucks, their noises. I was trying to use that to bend the wire, but then there's this heavy thing attached to the other end. I think I just have to hold it by the heavy thing. This is maybe not enough flux. It's kind of relaxing wearing the headphones. Too much upness, more down. That was a satisfying little flick. Alright, that'll do. Okay, so we've got that. Let's see, so we also need power. I don't think we care about network yet. This was 5 volts. And some clippy dudes for the SPI. I'll get my clippy dudes. Let's use this. So, and I kind of also would like a better ground. I don't know if I trust these grounds to be... I don't know, because like if any of these connections is not amazing, then, and that's my ground, then, you know, it can't hurt to have some better grounds. Let's just solder a group of like 4 pins to the ground here since it's super convenient. Nobody else is using that. Oh, it would be neat to show the current time in the chat window. I guess I would. In like UTC or just where it is here. I guess it does have a little tiny gray text for the time of, you know, timestamp for messages. There isn't much to compare it to if you don't have a clock and, you know my time zone and have all that handy. Tweezer time. Really, we just need like a whole operating system that runs inside the chat window. We're gonna have text editors and like a message of the day. Multi-user dungeon. Okay, depth perception fail. Let's just try and attack it somewhere. Now I will try to solder it slightly less badly. Wondering whether surface tension is just going to draw that pin right in, or if I'm going to have to push it. Maybe a little bit of pushing. That's fine. Not the best, but definitely fine. Heat up that ground plane, or no solder is actually going to stick there. So, like, I think, just to get back to somewhat higher level context, oh, it is a little bit weird to talk with the headphones on. I might take this off, but if the audio gets crazy again, please let me know. Yeah. There's like just slightly enough delay on the headphones that it makes it a little hard to think about what I'm going to say next. Alright. So I think the overall goal here was to end up with, you know, a material for a blog post, you know, about how on-chip or onboard buses work. And I guess from a perspective of security analysis, a lot of what matters are buses that have some kind of trust relationship. So one chip is getting code from another chip, one chip's getting data from another chip that isn't especially well validated. And you see this a lot in fairly subtle ways. One of my favorite kind of on-chip vulnerabilities was something, oops, that's getting a little, I don't think I quite lost that, but. Yeah, one of my favorite on-chip vulnerabilities was actually just related to the way that you access the registers on a crypto coprocessor. And, you know, if you perform just the operations that it expects you to perform, everything's fine. But if you write only part of a key, you can use that to exhaustively search a key without searching the entire key space. You can just search one byte at a time. Oh, Peter's asking me if I posted the previous blog post about the JTAG. So actually, one of my coworkers is going to be doing the blog post for that, so they wanted me to just continue doing some more videos. So I'm not quite sure if this one's going to be the thing yet for the next blog, but this one will either be the next thing or some investigation that turns out to not quite be the next thing. Yeah. Okay, so that's enough grounds. Let's just grab some pins from the SPI flash. So along those lines, I wanted to talk a little bit about just... let's just grab some pins from the SPI flash. What is that? So along those lines, I wanted to talk a little bit about just... What is that? I don't know where that echo is coming from. Oh man, sorry for the audio weirdness. I changed a bunch of things in the audio setup, and I think it might have been looping through some of the audio from the chat and like multiple other windows. That's super weird. Oh, is it playing in the OBS client? I used to not have speakers on this machine, and now it's like running all the audio. Let's try changing that. Oh, is it playing in the... Okay, resetting that. Oh, how do I turn that off? Oh, that's so weird. Yeah, the chat web client actually has audio this time, and it's auto-playing the video. How do I turn that off? I'm going to have to go in with CSS and... This is so weird. I'm going to have to debug this at some point. This is just really hard to do on the stream. If I reset it again, will it go away? I can still see it up there in the buffer. It's like barely on screen. Yeah, well, so this wasn't originally supposed to have sound. Maybe this is going to require figuring out how to disable that. Oh, I think actually OBS gives me an actual legit volume control for the browser sources, so maybe I can just turn that off pretty easily. Is that true? Where would that be? Live chat. I don't see an audio mixer for that. Yeah, I thought OBS was going to allow me to control the browser source as an actual volume source, but maybe it just plays using the system volume. I mean, one thing that I can do pretty easily is to just mute all the audio coming through this local machine. So I did that now, although that's not especially the solution that I want to use in the long term. Interesting. Sorry for the diversion. Let's see. I think we want to go back to this pinout. I should probably keep an ear on the headphones just in case. Alright, are we still good with the headphones? Alright, nice. Yeah, I mean, so if you send video to the chat room right now, I think it'll just be silent, but I will probably want to figure out how to actually route that separately. I should probably just set that channel to be off by default in Ableton, and I can turn it off in case I need it, or turn it on if I need it. Beep. Ooh, not that one. That's the one I have, I think. So we really just care about the clock signal and serial going both directions, but having chip select can be helpful, so if you have the pins on the logic analyzer, it's helpful to break that out too. And you definitely need ground, although we're getting it somewhere else that's hopefully a little more solid. Oh, where did our cat go? I kind of want to find the cat. I miss him. Oh, I don't want to disturb him. I think he's resting. He has that pile of fluff in the middle of my server racking mess all to himself. Okay, so here I'll be using the Salier Logic 16, but there are a lot of different logic analyzers you can use for this. In this case, for looking at the signals going between chips, it really helps to have something like a logic analyzer where you can just collect a lot of digital signals together. The alternatives might be something like a single USB to serial adapter for just communicating back and forth, or an oscilloscope. Sometimes you can find an oscilloscope that will also do the role of a logic analyzer, although those tend to be pretty expensive. If you're just getting started, something like this, or one of the many inexpensive. This is not necessarily the cheapest of even of the Salier logic analyzers, because this is their older 16-channel model. But something like these, or one thing that I've been really hearing a lot of good things about that I've been wanting to try is using an open source software toolchain called SIGROC on some really inexpensive logic analyzers that you can get on eBay that are actually sold as clones of this one. But if you use them with the open source software, then you can basically just use them as just basic 100 megahertz logic analyzer acquisition input devices, and not use any of Salier's software that they're usually charging you the premium for. Is that actually? I should make sure I remember which of these is ground. So there are a lot of ways you can get the signals off of this, but one thing that's really nice about a logic analyzer, you can see one single timeline with all of the different signals you're analyzing on it. So it gives you a good way to just kind of put together a timeline for what's going on. You can kind of reverse engineer how things are designed based on the order of the communications between components. Okay, we've got ground on the left, power on the right. So, and there's the silkscreen labels, right? Cool. So for that, I want the serial port on the logic analyzer and on a UART so that I can communicate with it and use the shell, but also see the timing of the boot messages versus the SPI flash. So I'm going to start out with the SPI clock, I think. So clock, pin 6. And let's do chip select next, maybe. That's pin 1. This will help us tell where the beginning of the transaction is and give us, some more timing hints that can be useful. Also, I don't know if the Salia software can reliably decode these without the chip select signal, so it can be helpful to have that for that reason too. So then let's do master out, slave in, which would be DI, or pin 5. These little mini grabbers are just the right size for these SOIC pins. Now DO is pin 2. Little dude. There you go. Alright, that's it for the flash. Let's have serial 2. That'll be these two. And we will just tap onto R and T on here, but leave room for some other pins so that we can add the serial cable there. Alright, and for the serial cable, I'm going to grab a little SI Labs USB to serial dongle from Adafruit, I think. Might be the easiest thing to use. This is the one I was using last time. It still has the connectors taped in the right order. So I have ground and the two serials in the right order next to each other. Right. This is a good time to tape this down because it's getting fragile. Pepper669 in the YouTube chat says that they found something cool called the Mocoder magnetic encoder. What's cool about it? Magnetic encoders are totally a thing. So we want some serial for the logic analyzer, or USB for the logic analyzer, USB for the serial adapter, and then we'll want some power, which I'm going to grab from over here. This one is like inconveniently positioned. All right. That is one of those connectors that just comes straight out of the board, which is a little inconvenient. Oops. There is like a special position this nut has to be in. That's interesting. Alright, that's a little inconvenient, but it'll do. mention, I think. Banana plugs. Oh yeah. 5 volts, 1 amp it says. We can do that. I guess we might as well plug this board in just because it's fun to see it flip around. It goes in this way. No, this way. Okay, so both of these want to be plugged into the computer. Let's give them a USB hub. So I've often found it really helpful to keep a USB hub right next to the device I'm working on, and then just plug as many of the tools as will happily share bandwidth into that one hub, which is a little easier with USB 3 hubs, although I don't have as many of those kicking around in the shop. This should be fine with the USB 2 hub. So I've got the logic analyzer and a USB serial adapter. And let's get that queued up on the computer here. So if we just take a look at our USB bus first, we should see the devices happily hanging out. Oh, good question from D.A. Beckham in chat. Can I put the microscope on the connection to the flash? Great question. Good question, actually. Can I? I mean, definitely if I handhold the microscope. Yeah, so they're just little tiny grabbers. These can really vary in quality. I think these are the actually kind of nice ones that come with the Salia Logics. You also see these mini grabbers kind of just end in these enormous tips with little slivers of copper that just bend immediately. So, oh yeah. I like that too. Extroverts have hardware social accelerators. Introverts have to do it in software. Yeah, that sounds about right. I often feel like I'm a little, I don't know, like a little alien inside of a human robot pulling the levers to operate it. Oh, let's go back here for a bit. I kind of wanted my others. There we go. That's what I wanted. So here is the hub I just plugged in. it's got two things that the computer doesn't really have a driver for right now. Is that right? I think this computer needs a driver for the prolific chip. Let's verify that. Oh, no, maybe that's it. The prolific chip is really bad. Like, it's the one that doesn't give the devices all different names, which is not so great. Let's see if we can at least talk. I like to use Minicom for this. And you have to tell it what device you want. I think we want the usual 115/200 with no flow control. So if you type, nothing will happen because there's no hardware loopback. But I think if we turn on the device, we should see some boot messages. So let's give it some juice. That looks like the wrong baud rate. Let's turn off the power. Yeah, maybe it was 57,600. I think that might have actually been in my notes from last time. Let's try that again. Power. There we go, there's the U-boot. So that's going to be reading from the SPI flash, I think. 7.2 megabytes will fit on that SPI flash chip, and then it uncompresses it. So yeah, we should be able to see all this on the logic analyzer pretty well. Let's get some more photos of this operating. Oh, we are not servo AF, not in the slightest. That's better. Okay, let's do that again, but with the logic analyzer running. Oh, this UI is starting to look a little dated on macOS. Alright, so we had not a ton of channels. We're going up to red and yellow. Yeah, so they had all the colors in here. That one. 50 megasamples is the most we got. So this should be clock, then chip select, not MIP select, chip select. Then let's get rid of this from earlier. MOSI, I think. So these are going to be the signals going full duplex in each direction simultaneously between the peripheral and the microcontroller. In this case, the host device, or the master in this terminology, I think is actually going to be a little bit of silicon that emulates a memory bus in the ARM by sending transfers to this chip. What is that? Minicom service. I wonder if that was a escape code getting sent back to the client and the client responding with something related to its name. And this should be RX and TX matching the silkscreen labels. So I'm going to turn off the power and let's just get a clean trace of it booting. And there's some power. That's going to be all of our SPI traffic right there. So this right there is going to have a firmware image in it. Like one way to read this is to just listen to it read it. And now we don't have any bus traffic during this part of the boot process. There's a little bit of data from the serial. System Architecture Department. Yeah, I agree with Sodium that the MDNS was separate from the Minicom 2.7-bit. Yeah, I think that's true too, if it wasn't clear. So I think soon we should have a shell here. Yeah, we already have a shell. So OV780 is going to be the name of the chip that we couldn't find a datasheet on. How are we connected to the OV780, first of all? What's in our kernel? We have UVC video. Is that for USB? What's on our USB? We don't have LSUSB. Can we get there in proc? Oh, that's a directory. Devices. It's been a while since I've done this without LSUSB. You could always compile LSUSB and stick it on there, but you can also do this manually by looking in /sys and /proc. Oh, actually, if they have this in /proc, the interface there is a little easier to use by hand. Ooh, yeah, this is easier to read. This is deprecated, but I still kind of like it because it's easy to use. Okay, I can just read that in the terminal buffer. Yeah, this is USB. So, and there's also USB audio. So this is all one device too. These are interfaces and endpoints. Yeah, so the camera is definitely high-speed USB, 480 megabits. So to sniff this, we would need to fairly carefully break it out onto connectors and then connect it to an analyzer probably. Or use a really fast oscilloscope, which we could actually do. Yeah, I don't know what's up with this manufacturer. That's actually the string too. So I think this is just a copy of somebody's example firmware. That's kind of sketchy. I don't know where the firmware for this chip comes from, like whether it gets loaded during boot here, so that might be another thing to look for. But again, that's going to be over USB. I think even the firmware loading would be happening over this USB connection. But that is going to be very similar to the process of just reverse engineering a badly or undocumented USB webcam chip, since effectively this is just a router with a webcam on the same board. So Mike Batiste is saying LSUSB. So that's what you would normally do if you had LSUSB installed, but LSUSB is a program that they would have no reason to include on this image. So the way LSUSB is implemented is usually by looking at the sysfs USB file system, but this proc bus USB devices is a little bit easier to read if you don't have any of the other tools installed. Robert's saying you can just cut the USB traces and connect two ends of a cable to it. That's what I was saying. I mean, but you'd have to do that kind of carefully for high speed. But yeah, that's what you would need to do, is a little bit of PCB surgery and adding some connectors or a cable. I would probably want to add connectors because adding cables there would be kind of unwieldy. But what else is here? We've got a hub. Is that the root hub? Yeah, that's the OHCI root hub. So I don't think we have anything else on USB except for the camera. Okay. So I think we're done. Let's take a look at our logic analyzer trace. So let's load this thing full of decoders. So RX and TX here are from the camera's point of view. So TX is it transmitting a bunch of stuff as it boots. RX is it receiving stuff from my keyboard as I'm interacting with it. And then here you can see some interaction with the SPI flash later on. We should see an MTD device, I think, that mapped to the SPI flash. What do we have there? I forget what the files are for MTD. Do I find? No, of course not. Oh, there are some MTD utilities here. Ah, there's a file MTD. There we go. Okay, yeah, this MTD device is the entire flash memory. So this is 8 megabytes. Erase blocks are each 32 kilobytes large. So we've got bootloader, config, factory data, and the kernel. So this is what we should see if we just scanned out the memory ourselves. And in fact, dev mtd 0. So let's save this trace because we'll want to come back to that. But just to do a really quick example here, if I start this recording, then if I wouldn't have XXD. There's no reason for that to have a hex dump. But if I just cat dev mtd 0 to, let's just send it to dev null so it doesn't mess up our console. And then let's see what that looked like in the logic analyzer. There we go. So let's add some analyzers so we can see what's going on more clearly. Async serial on 2 ends. 57600 baud. So can we read what this was saying? So that was just the enter at the end of my command. So I was typing it along slowly here and it was echoing it. And then I press enter, it echoes the enter. Then here's a bunch of memory transfers. Three. Is that a control C? I don't think it would be. I was expecting to see some escape code for a control C. And then this, what's our clock rate looking like? So 16.6 megahertz. Not bad. Definitely got some good hardware behind this, pumping the data around to keep this going. We can see the read block sizes here if we look at, I mean, it's not especially uniform, but we can start to see some structure here and how large the transfers are. Let's get an SPI decoder on this. This uses all the standard settings, I think. Maybe not. I might have just made a mistake there. Clock. So our clock idles high. That's this. CS is active low. SPI is still working. I don't know why it started at 85%. Is it done now? I really want this to be on just showing hex values. So I don't remember exactly what the structure of these commands is going to look like, but the first couple bytes are going to be the address, and then it's going to start responding with the data starting at that location in the SPI flash. So for most of this, the data going from the master out to the memory chip here, that's going to be all zeros, and the memory is going to be responding with its contents 1 byte at a time. But the header here, the microcontroller is first giving out a command, and then some of these bytes are going to be address. So we should see this starting at 0, and then, oops, the next command, that's a big burst read. So here you can see it stops the clock like it's waiting for some other action, like presumably waiting for somebody to empty a buffer in the kernel, waiting for the process to wake up, something like that. But it doesn't actually end the transfer, it's just pausing it. It doesn't end until way over here. And then the next transfer starts. Same thing, there's one command here, 50, and then it ends the command, and then it starts another one, 30, but this time, this is a different address. So I think it was just reading like 64K or something actually pretty large like that. Anyway, we could actually just save the contents of this from the logic analyzer, and that should match the file we're seeing. And that would be one relatively easy way to extract the firmware. But I think I'm going to actually save the extraction for a different video, since that's actually a pretty good self-contained topic. And I think we wanted to keep this one focused on just the overall how things are connected. So just back up a little bit and look at the circuit board. So most of the parts on here are just things that you wouldn't necessarily be interested in from a firmware developer or kind of software person point of view. It's stuff that's necessary to generate voltages. It's analog amplifier or comparator parts for the camera. But there are basically 3 parts on here that are super useful for anybody who's interested in firmware or security on this process or on this device. So there's the processor itself, which has a lot of internal parts. That's that RA-Link system on chip that has a built-in network switch. It has, it has a built-in Wi-Fi controller, so it might have, subcomponents that themselves are relatively sparsely documented and have potential security problems. Then on the board itself, you have this WinBond flash, which is mapped to an MTD device in Linux. That's what we're booting off of. The system on chip actually has some hardware support for that, so that's probably what we're just initially running code off of. And then that's then being mapped to a device file that Linux can use. And then we've got the camera, which is entirely just a USB device, and it might have its own internal oddities that we can get to through that USB. It might have firmware that the kernel is sending it, but then all of that is going to be happening over a high-speed USB link. And to debug that, the easiest way to do that is probably going to be to cut the trace and to add USB connectors to the circuit board so that you can get to both sides of that link. And then you can do things like connect another computer to this USB camera, connect this USB host to other devices like USB flash drives to get data on and off. You could just put a USB analyzer in between just to have it run normally but log all the traffic that you'd be seeing. And so that would be the beginning of another kind of long reverse engineering journey, unless you already knew, of some interesting technique that you wanted to use with the camera, perhaps, putting your own firmware on it if you wanted to get inside the camera. So let's see what this other capture ended up looking like. Oh, this needs analyzers too. It did not copy my analyzers from before. As you can probably guess by how these analyzers show up, well, maybe that was a little off screen, but there was a very short list of analyzers that are like what you would be most likely to use, and SPI and async serial are right up there. It is really common, but especially now that you're going to see much larger scale integration, and it's likely that things are going to be on one system on chip or on a couple of system on chips that have some high-speed bus in between them. And for those situations, you end up needing more complicated hardware. Okay, is our decoding working? Let's just see if the decoding's working right, and then we can actually walk through this. Great, I think that's good. Is this good? This doesn't look good. Is it still working? Oh, I think it's still working. Oh, it says 13%, 18%. Oh, there's Tuco. He's still in frame. Okay. This is getting a little better. So, let's look at the very beginning here. So we can see a lot of serial traffic here. These dots are the bootloader telling us that it's making progress. You can see that it has dots interspersed with a lot of flash memory traffic here. This is going to be when it's actually loading the bootloader and any initial stuff off of the flash memory. Then later on, what is it saying here? Here's Linux actually booting. So Linux version 2.6.21. It's a little old. More version info. CPU frequency 400 megahertz. I thought I saw a bunch of dots over here. There might have been some driver initializing. Oh, there's some dots. LZMA. Oh, this is decompressing the init RAMFS. Okay. So that's all happening on the CPU. So are we going to see some bootloading code? Is it actually running the first instructions right out of SPI Flash? That doesn't look right. I think the SPI clock phase is wrong. So this is telling you which clock edge is relevant, and I think I need to tell it that the rising edges are relevant. Now it's going to rerun the analyzer. All right. So this might be the command and an echo of the command, perhaps? I don't know how this protocol works. Let's take a look at the data sheet. A lot of these are really similar to each other, but I don't remember the details off the top of my head, so it would be helpful to take a look. Instructions. So, the first instruction, oh, is that still ASCII? 5. 5 is the first instruction. That's a read status register. That might just be making sure it's busy and, not locked or anything. So then 3, I assume, is some kind of block read. Oh, there's 3. Yeah, read data. Then we have an address in 4 parts, and then the actual data. So, yeah. So this is just reading from the very beginning of the chip. It would be hard to tell at this point whether it's... I mean, this is almost certainly a ROM copying data from flash. If it was executing from this memory, I would expect the access pattern to be not so straightforward. But this is a big block read. All of this is just contiguous. Oh, and then it jumps. What is this? 40. Yeah, so this is probably a couple of different sized reads operating under control of some firmware in ROM. So there's probably a ROM on this chip that's reading the first stage bootloader out of SPI flash and then running it. So what is this first little bit of thing that comes out of the serial port? U-boot. RA link, AP SOC, access point system on chip. So that is the first stage of U-boot right here. Definitely looks like it's being read by some ROM. Maybe a hardware state machine or something, but probably some ROM. Maybe we could take a look at how hard it would be. Okay, so, you know, like I've been saying, we have these 2 interfaces which could be interesting. There's the SPI interface that is trusted insofar as the firmware is loaded off of it. So that's obviously got a bunch of interesting things you could do there. You could rewrite the firmware. You could use it like we're doing right now to get information about what the processor might be doing, just, you know, as a side channel. So you can get some idea of, just by looking at the timing here, you have some information about what operations are happening kind of before and after interesting things on the CPU. You can get some idea of which things are cached, which things aren't. You can see, I mean, even just the fact that these reads are so long is interesting. So, I mean, this tells you this probably isn't reading cache lines. Like, if it was reading cache lines and running code, then you'd probably see several relatively small reads here, but instead you see something that looks like it's reading a header block and then reading the whole rest of the bootloader. And that might even be in the data sheet for the system on chip if we could find it. So then here's the U-boot message. Here's... oh, that's just a reset of some sort. It's probably resetting the peripheral. SPI wait nanoseconds. Great. It's telling us some important information. Here's a different command, F70. That one might be undocumented, or might not be relevant for this particular memory. Or I might just be decoding this wrong. That looks like I'm decoding this wrong. Oh geez, what is that? That looks like a high-speed mode is what that looks like. I might have reached the limit of this logic analyzer. So this irregular clocking here, it looks like I'm missing samples. So it might be actually clocking this chip at 50 megahertz or higher. And in fact, if it's saying something about SPI wait nanoseconds, then maybe it's talking about it just increased the speed of the SPI controller. So if you get into a situation like this, then you either need faster tools or a way to slow down the target. There might be configuration options that slow it down. You could try underclocking the entire system. Yeah, here we're just getting like less than half of each byte. Or you might just have to switch to faster tools. Since I happen to have a fast oscilloscope here, we can certainly demonstrate what that would be like. Let's try that out. Oh, that's a good question from Dan. Sorry. I think I might have seen this person's nick before as Dan, so I apologize if that's not actually their name, but D.A. Beckham says, how do you know if the code is encrypted and being decrypted by the SOC? That's a really good question. Sometimes you can get hints about that. The easiest way to tell is just to look at the code and see if it's high entropy, which would, like if it doesn't have much visible structure, like if you were to take that code and compress it and it wouldn't really get any smaller, then odds are it's either already compressed or it's, oh sorry, it's Don. Yeah, sorry to mess up your name. I didn't mean to, I'm just bad with human things like that. Yeah, the easiest thing to do is just to look at the firmware. The other thing that you might do is try to see whether there would be any hardware or software, like see if there's any space for the encryption or decryption to live. You know, if there's any software that's just taking some time to decrypt it into RAM, if there's any hardware that might be transparently decrypting it. Yeah, you can get some hints by just looking for the support hardware or software that would be necessary to make that happen. But definitely I think the easiest thing is to just look and see if it looks like they're trying to hide it. It's not totally foolproof, but it's usually by far the easiest thing to do. All right, let's get the Oscilloscope on here. So same deal, I'm just gonna hook this up pretty much right where we have the Salier. And here I'm using the built-in logic analyzer on this oscilloscope, which goes up to many gigasamples per second, which should be totally fine for this. I need a ground. All right, let's power this off. So if it turns out to be, you know, like less enough than 100 megahertz, then you could potentially use the Salier analyzer to get this signal if you just drop enough channels. Like I think if you get down to 2 or 3 channels, this will work at 100 megahertz. But you do still have to be quite careful. This ground is so far away. Let's use another hook for the ground. Tuco looks super comfortable. Let's try to keep these mini grabbers with their friends. I think these are really similar. They might just be different colors. Like I thought these were both Easy Hook brand. Maybe these aren't. They look like they're pretty much made just as well, though. Let's see, next wire. So yeah, one thing that's nice about just reading the data out of the SPI flash without the system involved, you can read it as slow as you want. Like, I think probably the way we'll do that, probably in the next stream, is to hook it up to an Arduino or a bus pirate or something along those lines and read out the firmware. And then we should see all these different sections, just like the MTD device in Linux reports. All in all, the easiest way to extract, all in all, the easiest way to extract that SPI flash image would probably be to find some way to kind of send a little like ASCII encoding program over to the device so that it can send it slowly over the serial port without it getting lost. I don't know what that noise is. Oh, that's a good picture of the tomcat. Thanks for the pic. Good night. I'm going to ground this one too. You don't have to ground all of these, but it's good to ground a few of them. Can't tell whether that's like neighbors dragging furniture around or Tuco's water fountain running on empty and making like gurgly, draggy noises. Alright, I think we've got it all transferred over to the faster scope. Let me go check on that. I might just need to pour a glass of water into Tuco's fountain to keep it from making noises. No, not the cat fountain, the 3D printer. That was a completely unrelated problem. That was the 3D printer getting tangled a little bit. I got some filament out from under the spool, and now it's fine. Got out those little boxes. Alright, digital stuff on the scope. Yeah, let's just run this on auto for a bit. I think we want the screen with the computer and the scope. And we're really only using like the first 6. let's just boot this thing up and start poking at the MTD device and see what the resulting stuff on the scope looks like. Oh, neat. I finally saw the response from a while ago where Pepper was saying something about this mocoder magnetic encoder. Apparently it's an enclosure for a common, I guess in this case it's an AS5600 chip plus a magnet. I think that might be the same one that this gimbal I was using on another stream uses. I'm going to take a look at that. Oops. So, that's interesting. It supports quad read. So we've got a shell. Let's just try reading from MTD0. And that was the whole thing. Let's do that again. Let's actually... There we go. So I think we want to trigger on... Let's trigger on D0. Maybe with some hold off. D0 is the clock. I just want to look at the read packets and get an idea what the timing is like. Did that not work? Huh. Is it? It couldn't be cached, could it? Oh no, I had the scope stopped. That explains it. This is pretty fast. That label is exactly in the way. Oh, this is only 16 megahertz. I thought it was going to go faster than this. Can I get a longer trace, maybe? I mean, we saw that during a particular point in boot. We didn't necessarily see it later. I don't know why it would switch back to a slower mode after going to a faster mode. I wonder if it's related to the size of the transfers. Do we have DD? We don't have DD. I probably can't do something that's a specific block size read easily. without sending it a binary of some sort. Anyway, that's not super important. We could play around with this if we sent it some more binaries or put a bigger system on it in general. I don't know how much it matters to me. It looks like here when I just read the device, it's giving me 16 megahertz SPI, but we were seeing something during boot that was going higher than 50 megahertz. I mean, these are pretty small packets, I think. I don't know. Would there be... Huh. MTD write in case we want to program firmware onto this thing. So, I mean, we could also probably get the file out in any number of ways. Over the serial port, or the USB, or the Wi-Fi, or the Ethernet. But anyway, I think that's going to be the wrap-up point for the stream. I don't want to get into one particular thing too much. I think I more just wanted to look at the actual interconnects on this device and see what kinds of poking around there might be. Oh, I just saw a good question from Cellular Interceptor on YouTube chat. Does it have I2C or JTAG? So I haven't seen any I2C devices, although that's a good question. I would expect that to be for like sensors or controllers of some sort. As far as I can tell, all the hardware on here is connected to GPIOs, or to the camera controller chip directly. The camera controller seems to do a lot of that. Like, it would be the kind of thing that you would normally find in a USB-attached webcam, and then the only connection to it would be over USB. As far as JTAG, there probably is JTAG. I have not looked for it yet. I was focusing on this stream in the connections between chips, but JTAG is certainly a useful thing to look for on these boards. Maybe I'll take a quick look for it. So, I don't see a lot of just spare debugging infrastructure on here. We did do one round of just poking around looking for debug headers on a previous stream, and aside from the pretty obvious serial header that we ended up soldering to, I didn't see much. There was some stuff that looked like it might have been test points, but I think it's more likely they were unpopulated capacitors. I see one test point. Oh, there's a couple. Maybe that's... I see like 3 test points. There might be enough for serial bar debug or something like that. There's those 2 vias. Don't look like they're intended to be used for connection, but they caught my eye. They're kind of larger than the others. Then this test point, which might be some kind of boot up mode. It's connected to a pin pretty much all by itself. Oh, that's going to the camera chip. I wonder if that puts the camera chip into a factory test mode, or allows you to program firmware on the camera chip. So, I think that might be it for this stream. No need to make this one super long, but just wanted to take a quick look at the onboard connections between the different chips on here and get an idea of how interesting it might be. A lot's probably going on between the USB on this chip and the main processor. It might be pretty interesting to find out where those are. I don't think we have actual data sheets for either of these, but we can probably find the USB traces if we're looking in the right spots, unless they're completely buried. That's going to the camera. looking likely that it's going under the chip first. Might be those two. The ones next to the text that says R75. Those are looking a lot like USB, aren't they? And there's 2 more test points, this time on the processor. Well, geez, I've got to at least prod one of those with the Oscilloscope and see if it looks like USB. That's a pretty easy test to make. Let's just plug power in and ground the Oscilloscope and go for it. Because that's something that might be interesting for another stream. So I'm gonna confer with my coworkers and see what would be the best thing overall, and we'll see what the next stream is going to be about. But it might be a different device. It might be going further into one of the things we've been looking at on this stream. I'm going to go ahead and take off these clips from the SPI flash since it's getting a little unwieldy. Okay. What do we got? Yeah, let's get this situated so that I can probe that while it's under the microscope and visible. At least in this orientation, the power cable is going up instead of down, which makes it a little easier to work with in the device. Yeah, those 2 test points are interesting. Those might be debug related. Those might be like SWD or JTAG. If we could find a pinout for this chip, then we could guess as to where those might be headed. So I'm also going to try grabbing this somewhere where physically there's room to add a connector in case we want to actually break these out. So this long diagonal section seems ideal. So I'm going to scrape off the solder mask there a little bit and we can do some probing. That is a dirty knife. I want to do these pretty close together. It doesn't really probably matter that much. Oh, there we go. I had to adjust the angle a little bit and actually pay attention to the right monitor. A little bit of isopropanol to clean that up. Right. Yellow probe. Do I have a good ground nearby? I do. Let's get that scope back up here. So for this, I'm not going to use the kind of long ground lead for this. I'm going to use the little spring. It's much nicer for high frequency signals. Oh, good question from Sodium. Is that just the lighting or is the solder mask really thin in some spots? It looks like overall this board has kind of a thin solder mask. It definitely looks like it's not covering this copper amazingly densely. It looks more, like that's more obvious in the microscope, but it's definitely still apparent just by the naked eye. So, I'm going to get this positioned and then see if we can watch it boot. That should be enough to get us started seeing a USB signal. So these are a differential pair. There are some signals in USB that are single-ended, but for the most part, we can see the whole protocol by picking on either of these wires. So I'm going to pick kind of arbitrarily and then power it on. Hey there, bootloader. I forgot there were LEDs right there. I don't know how long it takes to actually turn on the USB controller. I think it would have happened by now. Let's put this back on DC and look around. DC coupling. Sure. This is some intense lighting. Oh, is that it? That might be USB. Let's check the other one too. Oh, that's not so much. Oh, yeah, it is. Great. I just wasn't quite touching the trace. Great. I think that's what we're looking for. Oops. Are these microframes? So for USB 2, we should be seeing 8 of these per millisecond, I think. Yeah, those are microframe starter frame packets. So you always see that same microframe header, and then afterwards you see whatever transfers the operating system ends up scheduling on that microframe. Nice. So this is going to be super messy on the scope. This scope actually knows how to decode USB 2. I'm curious if it needs both signals or if it can do that from just single-ended. Oh, maybe it doesn't need both. Whoa, that's cool. That's the microframe number in the starter frame packet. I don't know why it's not oh, there we go. Start a frame. Oh, that's beautiful. Oh man, I didn't even know, I've never seen anyone use an Oscilloscope that can decode USB 2. This is really cool. So I can get starter frames off of that. Can I get starter frames off of here? I might have to tell it to invert. Oh, I guess it figures it out. Great. Oh, that is so cool. So then after the starter frame, we're just going to get all sorts of other data, which is going to be kind of annoying to decode without more tools, but this is really neat. Can I trigger on specific transfers? Also, I don't know if it's reading video or not yet, but if it is, that would explain these kind of chunks every so often. Those might be actual video packets coming back from the camera. Anyway, that's what USB 2 looks like on a scope, on our really fancy scope. That's pretty cool. Can I trigger on these packets? Start a packet? Oh, I can trigger on data packets on specific PIDs. Oh, yeah. Come on, come back. Did I just sort out the USB? There we go. I think that C might be the endpoint that I'm receiving the packet on. And then we have the actual contents. I think that's video data. The stuff down here, these are probably polling for these will be polling for some kind of data coming back from the video chip to the host. Usually that's flow control or buttons. Like a lot of webcams have buttons that you end up having endpoints for HID or something like that. So the host is periodically polling to see if any of the buttons are pressed. I'm hearing suspicious noises from the 3D printer closet again. Okay, I think that's better. I think it'll be fine. So, I think we're wrapping up the stream for today. This was kind of some exploratory work, and I think we'll pick a topic to dive deeper into next time. That might be the USB, that might be the SPI, that might be something kind of different. Hey Tuco, aren't you on this table now? Well, we found the cat. Thanks for hanging out, everyone. Next time we might have some more investigation on this, and as always, there are a range of interesting projects to hang out with on this channel. Tuco seems to like some of my logic analyzer accessories. I better be sure to put those away. Alright, happy hacking, everyone. I will see you on the interwebs.